All right, so today is an exciting day for me because there's a lot of neat things in this lecture about calibration techniques. So you've done calibration in several classes. So tell me the classes. I think probably quant and instrumental. Is that the only ones? Or
biochem?
You did some biochem. So what kind of calibrations did you do for those three? So you've had at least 3 courses where you did calibrations.
Like for what instruments?
For what techniques of calibration? So maybe the question I'll ask you after I get to the slide where there's different techniques, and then you can identify which ones. So we're going to be talking about the calibration techniques and quantification today. So standard additions. Okay, very good. That's one of the ones we're talking about. Any others?
Serial dilution.
Which one?
Serial dilution.
Serial dilution. That's a technique within all of the calibration techniques. So you use that within all of them. External standards and internal standards. So those are the 3 that we're going to focus in on, and we're going to get into the statistics behind those. So we're going to apply what we just did with the statistics and confidence intervals, null hypothesis, and stuff like that, and we're going to put it into these calibration techniques that you've touched on in other courses. So that's great. All right, let's try this again. Let's go. And so we have the dependent variable and independent variable. Typically, our concentrations are those independent variables. Those are the x-axis, the horizontal axis, and then the y-axis is the dependent variable. So the signal that we get is dependent upon our concentration. So those are the 2 variables that we're discussing. There's another term that we talk about that's called linear dynamic range. We'll see this on the next chart. That is how many orders of magnitude we have on the response axis, the y-axis. So basically, how much signal can your detector detect and stay in a linear manner? Okay, infrared is notoriously small, so it maxes out at an absorbance value of about 1.5, maybe 2. You start getting above 1.5, the response starts to get nonlinear. Okay, so that goes from 0 to 1.5. That's barely like 1.5 orders of magnitude. So orders of magnitude are how many powers of 10 you have. But then again, it's very stable, like infrared. So the difference between 0.01 and 0.02 is a real significant difference. So really, you can detect, in terms of infrared, small differences in intensity. It just doesn't go very high. So you might, because you can get 0.02, 0.01 precision, you really have, even though the like ones place goes 1 to 1.5, 0.01 is a significant difference. And so you can tell probably 3 orders of magnitude. So 0.01 is a significant difference in infrared that's repeatable. And so you can get 0.01, 0.1, and 1. So you have 3 powers of 10 or 3 place values. That's what we mean by orders of magnitude. So in infrared and a good detector, you can tell the difference between that 100th place reliably. And so you have 3 place values, so that's 3 orders of magnitude, 3 powers of 10 that you can have on your y-axis that are reliable. Things like peak areas in GC, they might be different in the thousands, but they can go up to the millions. And so you just count how many place values you have in your linear range. And so if the sort of baseline noise is in the thousands, then anything lower than that you really can't reliably detect. So let's say your blank value comes in at around 1,000, but then your maximum value is 1,000,000. So you have 1,000, 10,000, 100,000, million. So you have 4 orders of magnitude, 4 place values that are significant. And so that's what we mean by this linear dynamic range. So there's part of these terms too that I've already used, like I used the blank value. There's the limit of quantitation, and that's the smallest significant concentration in your linear dynamic range that still has the acceptable statistics or acceptable uncertainty. You have the limit of detection. Now that's the smallest signal above background. Notice the differences in these. The limit of detection is the smallest significant signal where you say, okay, we've detected something. Well, you can't reliably quantify it. Okay, you could tell me what concentration that may represent, but you're not certain about it. The LOQ is when you become certain. So there's detection down here, and then up here is the limit of quantitation, where you can be certain about the concentration. Then there's the correlation coefficient, which we will discuss later, but that's that percentage of the scatter in the data that's captured by your model. And then you have other terms too, like blanks and controls, blind controls, cal checks, replicates, duplicates, spikes. These are all of the vocabulary of analytical chemistry. And I've got a page from the textbook that's available on Blackboard. And these are some of the, I just wanted to clear up the differences between replicates and duplicates. Okay. So this is sort of showing like a sports testing lab where they're testing for anabolic steroids and so on. But also at the workplace, I noticed whenever they were taking drug samples, because at Pantex, everybody was in the drug sampling program. So you would get a page. We used pagers back then. Cell phones weren't allowed on the plant site. So your hip would buzz, pick it up, and it would say, report to medical. So you had to go to medical within 15 minutes to give a drug sample. So the worst possible scenario is to come right out of the restroom and have your pager go off, and you're like, I just went. So you had to go over there. You had to report within 15 minutes. But if you needed to sit there and drink water, read a magazine and wait, you could do that. But sometimes you had to do that, and then you had to go to the bathroom so you could go in and give them a sample. But immediately they would take that sample and split it into two, and they would put a little temperature tape on there to see that you didn't like put a fake sample in there that you had for just those occasions, and so they measure the temperature, and then they labeled it with barcodes and so on, and they had the split. So they would send one off and keep one in the refrigerator. So this is what's being shown here. Okay, and so that split sample are called duplicates, and then within that, so like when it comes into the lab, then one of those duplicates is tested, and it's split into three, and they run 3 of those. And so these are called replicas. So the duplicates are the split right here, and the replicates here are these. They're split at the lab. So they're the one of the 2 duplicates, and then they're split into replicates. And so they're split at the lab, and since they're from the same source that came in the door, they should be very tight. They will tell you your sort of the instrumental uncertainty. So it comes in, and the only difference in those is just how you handle the samples within the lab. Now, if one of those hit high, say it registered a drug or something of that sort, then they would call back to the plant and say, send us the split. And so there was, again, trying to get away from that 95% confidence. Being 1 out of 20 would give you a wrong response, right? So if they analyze this and so it shows high, just to check again, because they're about to get you in a lot of trouble, they call back for the split, and they send the split, and they analyze it again. So this is the same sample, but they analyze it again. If you get hit again on the split, then they're pretty confident that you had drugs in your urine. So this is a horrible calibration curve. It's in the book, but but anyway, they put it in the book to show all the problems. The data, what's horrible about it? I won't say much about it. What do you see with the data points? Yeah, it doesn't look very linear, does it? So, if I were to just connect the dots here, that goes up like that and over here like that, that's pretty ugly. Okay. Now, if we kept collecting data, up here we have saturation, and so our data points would look like this. And why would it taper off? Almost every calibration curve has a point where it tapers off. Yeah, and think about what's happening over here. This is the abundance of the material, and you're putting more and more stuff on the instrument. Eventually, it just can't handle anymore, right? Think about an absorbance measurement. So your sample goes in, it absorbs light, eventually there's no more light left, right? The more sample you have, the more light's absorbed. And so you're looking through a sample that's completely opaque now. And so your detector signal is going to max out, It's actually going to minimize out, but you're taking a ratio of that versus the light without the sample, okay? And then you're taking the minus log of that. And so the minus log flips the peaks up. And so the peaks get higher and higher the less light there is. But eventually there's no light. So the peaks can't go any higher because there's no light. And so that's why I say, 1.5 absorbance units. Since it's a log scale, that's like 1,000th of the light coming through. Okay, so there's saturation. And so then this, before it saturates, and then after you get out of the noise, that's the linear range. So that's what we mean by this, linear dynamic range. You might be able to put like a polynomial on there. Sometimes you can add a quadratic term and kind of capture a little bit more of the range. And so if you're using a quadratic model, you can extend the linear range. And in that case, it's not really linear, but it still follows your model. Okay, so that's, even though it's not, quote, linear, if it's still following your model with acceptable statistics, that's okay. So you could have like a 3-parameter calibration curve, which would be a quadratic equation. And then you would have to still determine, at what point, like if you add this data point in, then your R squared is trash, and then your p-values for your coefficients go away, and you've gone too far. And so then you would take that point out, and then you would just use these points. And as long as you've got good p-values and good R squared values, then you're able to model that last little curve of light, but not too much. Then we get down here in the noise. Oh, what I was saying about orders of magnitude. So this would be the difference between here and here. Okay. So how many powers of 10 do you have here? In this range here. That's what we mean by dynamic range. And that's that dynamic range. That question, okay? Does everybody understand what I mean by powers of 10? I'll try to relate it to place value, from thousands to millions was 4. Then we get into some really terrible limited detection. The noise looks crazy. I wish they hadn't done like a line, because the line looks ridiculous. They could have just put lots of data points, here. So the data points down here look like there's no trend at all. And then all of a sudden we see a trend. So you can come down here. Let's say we have our blank value here. We've got, some other values here, but there's really no linear trend until we get up here. This is the beginning of the linear range. And so that's what we call that limit of quantitation. Okay. If we were to take our blank value here at 0 concentration, 3 times that would be our limited detection. So that's a good rule of thumb. So LOD equals 3 times the blank signal. So this is what they call general or good lab practice or general lab practice. And then some people will compute the LOQ. Others will say that it's 10 times the blank signal. Okay. So it just depends on the lab. So you say 10 times. And you would just determine which one your lab wants to use. So we'll see lots of calibration curves today. So this correlation coefficient is related to what we said, the amount of scatter in the data that your model covers. So here's the data all over the place down here. You can draw a line through anything, but if you calculate the R-squared value, this one, it's going to be 0. And then up here, you see how beautiful those data points are captured by that line. It goes through all of them. So that'd be a perfect correlation where 100% of the scatter is captured by the model. Now, where does R come from? It comes from these calculations. So here's R-squared, and these are the sums of the squares of the data or the sums of the products of the data. So this is called the least squares method or sum of squares method. And you can see how these are defined. So this is the x-axis values times the x-axis values added together. So this is the sum of all of the individual x data points squared minus the sum. You sum them in together before you square them. Look at the parentheses. So here you add all of those x values together, and then you square them and divide by the number of data points. Okay. And so that's the SXX value. This is the SXY value. So you have x times y. So the sum of the x values, add them all up, and then you have the sum of the y values, and then you multiply them and divide by n. And then this is, you multiply them before you sum them. So again, you could do all of this in Excel, and you could come up with the x, y values. You can just do the linear regression, and it does all this for you. You could do a trend line, and it does all this for you. Okay. But sometimes you'd like to have the equations in order to calculate these on the fly. So there's some rare occasions when you might want to do that. One of the times they asked me, we were working on this problem that they had on the manufacturing line. They had made some epoxy and they had set this part, and then later on they come back and the part had fallen off. So they had just glued it onto the thing that they were building, and it cured, but it didn't cure right, and it fell off. Well, this was a real big problem. So they brought us in from the science division and said, we've got to analyze this epoxy. So they said the technician must have not stirred it right. So they didn't get the epoxy. It's a 2-part epoxy stirred well. And so the part of it cured and part of it didn't. And so the part fell off. So they tried different ways of stirring, and they let it cure in the little cup. And so I had all these little epoxy pucks that I was supposed to analyze on the infrared to determine which ones were mixed well and which ones weren't. Okay. And one way you could determine if it was mixed well would be the hardness value. So you set it on this little pin press, and you press this pin into it and see how much pressure it takes to dent the surface, and that is the hardness value. So they had like 7 or 8 pucks that they had hardness values on. So those were my my independent variables. So I had hardness 1, 2, 3, 4, 5, okay, up to 7. And then I had infrared spectra for all of those. Well, which peak in this spectrum, you've seen an infrared spectrum, very complicated. Which peak is the hardness peak? But who knows, right? Who knows? And so what I did was I had a column, I had a spectrum for every hardness value, and I wanted to find the peak that correlated to hardness the most. So I have probably 4,000 data points or more, and I have to do 4,000 linear regressions. So that's the time when you would use these equations, right? So I just went over to the right and made a column of sum of x's, and those were the sum of my hardness values. The sum of the y's was that particular wavelength, okay? And then I calculated the sum xy was the hardness values times that particular wavelength, and I did all of these equations here, and I was able to calculate the R-squared value at every wavelength. And then I just plotted that the highest R-squared value was the best place in the infrared spectrum to correlate with hardness. And so I was able to do 4,000 linear regressions on the fly in Excel, piece of cake, I have the equations, and find the wavelength that would tell me which puck was mixed the best. Okay. And so that was a way that I solved that problem using these equations, because I didn't want to go through, data analysis, regression on every wavelength. There's no way. Okay, so that's another term for that is chemometrics. That's a kind of a crude way to do chemometrics, but it worked. Okay. Once you have the sums of squares, you can do the y value, the model at mx plus b, and so you can solve for m here and b. So that's pretty straightforward. So let's do calibration examples. There's 3 calibration examples here. We have the external standards, and that's the simple calibration method you've probably used, maybe even in some of your Gen Chem labs. I think there's a spectroscopic lab in Gen Chem where you use the Spec 20s. And then internal standards. I'm glad to hear that y'all covered internal standards. You said it was in biochem? What was that?
I think that was covered.
Was that in quant? Okay.
And I think later in the show.
Do you remember what instrument you did with the internal standards? Instrument that was on? I'm always curious to learn what's taught in the other courses. Yeah. The standard. Oh, really? Was it?
I know we talked about internal standards, but I don't know if we actually did.
Okay. Okay.
Yeah.
What about?
Yeah. Instrumental.
And then standard additions. Do y'all remember which one that was? Yeah. That's where you actually add. You take your sample and split it into several aliquots. Instrumental. Okay. So we'll analyze these again. It's always good to review. So we'll show this same analysis using all 3 techniques, and we'll see why you would choose the different ones. So that'll really hammer home how you make a decision on which one to use. You have 3 different choices. How do you choose? Right. And so we'll talk about that. So in the internal standard, a different standard is added to the analysis samples to provide a ratio signal. And then in standard additions, the analyte is added to varying amounts of the actual sample matrix. So if it's a blood sample, you break it into 4 aliquots, and then you add varying amounts of standard to the actual sample that you're analyzing.
Can you mix methods?
I don't know.
Theoretically, you could do standard additions as well as using external standard.
Yeah, you could. And just analyze it both ways, just to see which one is better. Yeah, so it may be. Yeah. Okay, so then here's this external standards analysis. So what we've got is sort of a sample to check our lab. We've got an analysis of blood that contains 125 parts per billion of cocaine. So we've put that amount in the blood. And now we're going to analyze it and see which method gives us the best answer, right? So we know the answer in this case. A lot of times you wouldn't know the answer, but in this case, we've set it up to where we know there's 125 parts per billion. That allows us to check our accuracy. Okay. We could check precision without that. So we could have a sample of blood that has an unknown amount of cocaine in it, and we could run all of these and see which one's the most precise method. It keeps giving the same answer, but that wouldn't tell us if we're accurate or not. And so this is a way to check the accuracy, is to dope it with a known amount of the drug. And so this is the first calibration method you learned. And the key for external standards is that you have to have minimal matrix effects. And so in this case, what do we mean by matrix effects? What's the matrix of this sample?
Blood.
Yeah, blood. And so in this case, let me find my pen. Yeah, here we go. So the matrix, this is blood. So we know from the beginning that this is going to be serious, because what does blood contain? Do y'all know? Let's just kind of list out the things we know.
Plasma.
Plasma, what is it? What's in the plasma?
White blood cells.
There's cells. We'll just say cells. There's white blood cells, red blood cells, and so on. So that's part of it. But then all the other things that are just in the plasma. Like there's things called platelets. I don't know, but there's platelets. Okay. There's, what else? I mean, there's enzymes running around. Yeah, enzymes are a real problem. What do? They break things down, including cocaine. There's metabolites. Enzymes do metabolism, and so enzymes and cells and platelets, whatever those are. Okay, so showing my ignorance. Okay, and so the sample is blood, but the external standards are various amounts of cocaine made up in an organic solvent like acetonitrile. And so that's probably gonna be a problem. So we know right away that's may cause problems. But we're going to do this anyways to see where those problems show up. So the external standards are varying amounts of cocaine in organic solvent. The organic solvent is not blood. This may cause problems. So here's our analysis. So let me walk you through the different parts. So up here we have our cocaine standards in a solvent matrix. So we put in parts per billion cocaine and acetonitrile and ran it on the GC, and we get the peak areas here, 20, 50, 100, 250, and 500. And so we plot this, and it looks really nice. So here's parts per billion cocaine, and here's the area counts of our method. Nice, beautiful line. R squared is great, 0.9994, so 3 nines. I mean, it's even better if you have 4 nines. But still, that's pretty good. It's respectable. And here's our slope and our intercept. But once again, we don't have the uncertainties on those values. So we don't want to just use a trend line. We could find out, we could use this equation if we ran another sample of our actual sample in here. We would get an area, and we could come over and we could use that equation to tell us how much parts per billion cocaine we had. But we wouldn't be able to calculate the uncertainties. And so we want to always do that. So you want to do not just the trend line, but take your data, go through the data analysis, pick the X input is here, the Y input is there, and hit go, and you get the ANOVA output. Okay, so here's your R squared value. It matches the one on the chart. That's nice. Here's the intercept and the slope. So these are your chromatographic signal peak areas. This is your linear fit, and here's your B value and your M value. And the nice thing from the regression analysis is that you get the SB and the SM, and so you can calculate your uncertainties. You also get these P values. So I've highlighted the P values, and can you recall what those tell you? So one is yellow, the other is green. The yellow one's, if you can't see it, is 0.47 or 0.48. And the green one is 6.2 times 10 to the minus 6. Which one's the good one? 10 to the minus 6, right? And P is that letter P is a hint. Probability. So the P values are probabilities. They're probabilities that the null hypothesis is true. So we've got to know what the null hypothesis is. So the null hypothesis is that M and B are equal to 0. That's the null hypothesis. Okay. So that means that if M and B are not equal to 0, that it's just because of noise, right? The null hypothesis is there's 0. If I look and I see a number that's not 0, I need to test to see if the noise in the data could have given me that number, right? So this is the probability that the intercept B is 0. There's a 50-50 chance that B is 0. And here there's a 6 times 10 to the minus 6. You don't even need the 6, just 10 to the minus 6 chance that M is 0. And you can look at the chart and you can say, yeah, absolutely, M, all the data is telling us that slope. M is very confident. But the intercept, that's the up and down on this whole line, And it's coming in at 1,200, which is a big number. How could we say that that's 0? Well, look at the range. It goes up to 250,000. So that range is so big that 1200 is minuscule compared to the range of the data. So when we have things that are up to 250,000, 1200 is really not that much. So yeah, it could be zero actually. And so that's why this probability that it is zero is really high. What would we say, like, what's the cutoff p-value when we would say that the probability is too high for us to accept that p-value?
0.06.
0.06 or 0.05 or above, yeah. At 0.05 would be our alpha. And so we're comparing this p-value to alpha. So for 95% confidence, alpha is 0.05. And it's sort of a judgment. I don't know if it would ever be exactly 0.05. You know, there might be some decimal places. But if it's greater than 0.05, you would say reject it, reject the null hypothesis on B. If it's less than 0.05, you would accept it. So if it's 0.04999 or whatever, then you would accept it. It's probably unlikely that it's going to be 0.05 with all zeros. So if it's 0.050001 or whatever, it's greater than 0.05, and you would reject it. So that seems like a really harsh test, but that's, you know, if there's even a 0.05% chance, a 5% chance, sorry.
Why would you reject it?
Pardon?
Why would you reject it?
Because it's not statistically significantly different than zero. Big, lot of syllables there. We're testing the statistical significance of the B-value.
Does that mean you failed to reject it?
Pardon?
If it's greater than 0.05, does that mean you failed to reject null?
No, if it's below 0.05 or 0.05 or lower, we fail to reject it. Okay.
Sorry.
So we accept it. If it's 0.05 or lower, we accept the B-value. So we fail to reject the null.
Yeah.
Yeah. No, we accept the null hypothesis if the probability is greater than 0.05. Yeah. And so we're saying that this null hypothesis, that B equals 0, this is greater than 0.05, so we accept the null hypothesis. And we set the B to 0 and redo the regression. Does everybody follow that? I kind of got confused. So if this is the null hypothesis, if this is greater than 0.05, we accept the null hypothesis, and then we set B to 0 and redo the regression. We do the same thing with M, but in these calibrations, your M is probably not the thing in question because you put in different amounts and you have a really nice slope that has really good statistics.
So just to make sure I'm getting it right.
Yeah.
So if it's greater than 0.05, accept. If it's
Yes.
lower, reject.
Yeah, that's right. And so a lot of times they say, they instead of saying accept, they say fail to reject. Okay. So why they say that, I don't know. But it's because it's a nuance to say you can't say anything's true. You can just say I fail to reject that. I can't tell you it's true, but I can fail to reject it because of this criterion. So it really sounds fishy, you know. Someone accuses you of something and you say, well, I fail to deny that. I'm not going to tell you that's true, but I fail to deny it. And so anyway, this doesn't sound really reliable, but that's the way we do it. So so that's the null hypothesis on B. So let's redo this analysis. And so here's again those equations. This gives us our sums of squares, the R squared. Here's where the SB comes from and the SM. So these are your uncertainty values. I just throw these up there just so that you can calculate yourself the uncertainties in those. Okay. This uncertainty of the whole regression, the only reason you have to calculate that one is because it shows up here in SM and SB. So you have to calculate that before you calculate the others. Okay. And it's just using the same kind of terms, SXX, SYY, and the sums of the different values. Okay. Looks pretty ugly. It is, but that's how you do it. So we go through the regression analysis again, and down here at the bottom, there's a checkbox, and same with the trend line. The checkbox is set intercept equal to 0. So you set that intercept to 0 and redo the trend line. You could set that intercept to 0 in the dialog box that you use for the data analysis regression tool. And then you end up with this output, and you see how the intercept is 0 and all these are not applicable. That's what NA stands for, not applicable. because you've forced the intercept to be 0, so you're not calculating any statistics for it. So when you see this, you know that it's been set to 0, and you don't have any uncertainty associated with that because it's defined as 0. And so now we can calculate our concentrations. So we have this equation, y equals 420 times x. So you could reverse that and take your y value. And so if we put in a check sample of our blood, here's the signal that we get from it. So that's the sample area. Now, in this particular analysis for all of our uncertainties and everything, we just ran one check sample. We could have done 3 and gotten statistics on our y value, but it's just a single measurement of the blood sample. Here's our calculated parts per billion. So that number divided by 420 gives us 68.2 parts per billion. And the uncertainty is calculated from these uncertainties up here. So the standard error in SM. And I'll show that calculation in a second. But that uncertainty compared to the calculated parts per billion is a 1% coefficient of variation. But the true value is 125. So you see this is quite low. It's 45% low. And again, it's because well, you tell me why. Thanks for doing that. We know there's 125 parts per billion in our blood sample. We just ran it and we calculated the concentration and it came out to be 68.2. Yes?
Oh, it could be because the intercept was at 0.
Well, we could test that. So let's go back here. We could test that here and calculate our concentration with the intercept not equal to 0. And this is pretty close to 420. All right? We would subtract this from our check sample, and that would reduce it some. And then we would divide by a smaller number, and so we get it back up, and it's going to give around the same calculation. So, but that's a good thing to check. And we would go through and do the calculation with the intercept and see what we got. And we would see that it gave a similar amount of around 68, 67. So, but that's a good thing to check. It's something else. Something else is going on.
Between blood and acetonitrile?
It's related to that difference between the blood matrix and acetonitrile matrix. Okay. We talked about enzymes in the blood. So this could be some metabolism action on the cocaine in the blood sample that's not happening in the acetonitrile. So we got to figure out how to take that into account. Okay. So our squared actually went down a little bit. Here's our uncertainty. So let's see. This is with the, so this is calculating the uncertainty. We did this in class the other day when you have a y value and an x value. So let's go ahead and do the propagation of uncertainty on this one. So this is using the intercept. So we have our calculation, y minus 1213 divided by 417. And so we have the numerator is equal to 28,632 minus 1213. So if you're doing this on your calculator, please call the numbers out to me. And then we'll just have the second person check that number.
27419.
Okay, and so that's the numerator. Then what's S numerator? So S numerator is going to be the square root of SY squared plus S, what do we want to call the sample? Oh no, SB squared. All right, so SY, because we only have one aliquot of Y, is going to be 0. We don't know it. Okay, and so it doesn't add to our uncertainty at all. So this one is 0. And so the S numerator is going to be SB, right? It's the square root of SB squared. So this is the special case when you don't know the uncertainty in Y. If we had done 3 Y samples, like we did the other day in class, we had 3 Y values, then we would have an uncertainty in Y. But in this case, we don't have an uncertainty in Y, so that one's 0. So our uncertainty for the numerator is SB. Now we have our division and subtraction. So the X value is equal to the numerator, 27419 divided by 417. I think that one is actually written out. 65.8. Okay. And that unit came from the slope, which was counts per unit area, per parts per billion. And so I haven't been using my units, so it's bad. And then SB, how do I calculate? Not SB, X. Is going to be the square root, it's going to be X times the square root of the RSDs of these things. So I have the 27419. What's in the numerator of that one? It's the uncertainty for that numerator. And that's going to be SB. So that's 1500 squared. And then SM over M. So 6 over 417.
.72.
Yeah, 3.7. And it gets the units of X, whatever X's units are. So X is parts per billion, so that's the units that we get. So this is where those two numbers came from. I just wanted to calculate them slowly by hand so you could see how the propagation of uncertainty went through this. The only difference from what we did the other day was that we had 3 Y values the other day. This time we only have 1 Y value. This makes it a little bit easier. We didn't actually have to do this calculation of uncertainty because it was simplified because one of the terms was 0. And so then the CV is going to be 3.7 divided by the 65.8 and times 100%. So it's 6%. And the true value, 125, our percent error is minus 47. So this was kind of like your question about if we included B, this is the results that we would have gotten. So including B, we had an uncertainty of 6%. Look what happens when we got rid of B. Okay, when we got rid of B, our uncertainty dropped to 0.6%. So just because we had a better R squared with another variable, so if we included B, our R squared was better, that tends to make people want to use it. But it actually, in trying to model B, you're actually introducing error in your equation. You're less certain about that equation because you're trying to model something that's not a real effect. And so if it can be eliminated, statistically eliminated, and then you've got your one variable, M, that you're statistically confident in. And a lot of times that's what happens. So our uncertainty decreased. And so that's good. We went from 6% uncertainty to 1%. We're still off by about 45%. So let's try the next calibration. And let's go to internal standards. So this blood versus organic solvent is a matrix mismatch. So we could put an internal standard just to see if that improves things. Probably not. But anyway, a standard not cocaine is added into the analysis aliquots to provide a stable ratio signal. So we're going to put this standard into all of our calibration standards, and then we're going to also put the same aliquot into our blood sample. So we're going to have an internal standard that we can ratio all the signals by. And so this requires a selective instrument that can see the two compounds and not have them interfere with each other. So you have to do this maybe like in a spectroscopic technique, you can use internal standards if you have peaks that are separate from each other. You can do this in atomic spectroscopy if you have two metals. You have a metal 1 as an internal standard and metal 2 as the one that fluctuates. And then in GC, if you have, or LC, if you have chromatographic separation, you can put your internal standard in if it comes out at a different retention time. It's always best to have it be kind of close to your analysis, just so that you can, you know it's behaving more similarly the closer the peaks are. So here's our internal standard calibration curve. Notice we have the same cocaine standards that we have, but then we have this internal standard here. So this is the 75 parts per billion xylocaine were added to every one of those calibration standards. Look at it, that we added the same amount to the differing amounts of cocaine. And so we're doing a ratio of this signal, parts per billion, peak area, divided by the peak area of the xylocaine. And so our peak area ratio changes with respect to the initial concentration. But one thing that this does, this internal standard, and this will show you how it works, and that is internal standards are best if you have sample-to-sample variation. So if there's something about your technique that causes sample 1 to act differently than sample 2 or differently than sample 3. And in manual injection, that's almost always the case because we're just not that mechanical. We stick that injection in, let's say GC manual injection, you stick it into that hot area and you squirt in the sample. And it immediately boils and goes onto the column, okay? But if you go in and you're slow, some of it's boiling out of the needle as it goes through, or maybe you punch it a little too soon and it starts coming out before it's through the septum. There's a lot of things that can go wrong with your technique. And so you may be good, but there's going to be more variability in your manual injection than there would be with an auto sampling injector that does it all, mechanical the same way every time. So if you're doing manual injections, you almost always have to do internal standards. Because look at the internal standards column. I put in the exact same amount of xylocaine in all of my little samples with a really reliable pipette, and it's jumping around in the second digit. So it's limiting my sig figs to 2 digits because the uncertain digit is in the thousands spot, even though I put in 75 parts per billion in every sample. So that's showing you I have sample-to-sample variation. So this is going to get rid of the sample-to-sample variation, but it's probably not going to get rid of the matrix effects. Okay. So I'm giving away the punchline, but anyway, it helps reinforce what this is used for and why it doesn't fix things in this particular sample. So we do the regression analysis, and again, our intercept is no good because this is greater than 0.05. So I guess we accept the null hypothesis or fail to reject it, and we throw B out. Okay, we reject the null hypothesis for M and keep it. Okay, so we're keeping M because it's statistically significant. And then here's our check sample area. Here's the internal standard that we put into our blood sample, and here's the area ratio. And notice that that's what we're plotting, the area ratio versus parts per billion. And so this is what we calculate, 126 parts per billion calculated, and 3.1 parts per billion. So that's pretty good. This ratio signal seems to have corrected quite a bit. We're still not quite there. Our uncertainty is 2%. The true value is 125 parts per billion, and our percent error is 0.8. So that's fantastic. That's with this model of keeping B. So look at our 95% confidence interval. It goes down to 120 and up to 132, and that captures our true value. So that's fantastic. Okay. But we've got a problem because we've got a B value that we're using in our model that's not statistically significant. So we really should take that out. Okay, so let's take that out. So we redo the regression analysis. We only have the slope now. Here's our check sample, our internal standard, the ratio. We run that through our model, and we get 127.7 and our CV is improved 1%. And here we have our upper 95% confidence interval is 129.5, and our lower is 125.8. And that's sad because now it doesn't contain the true value. So we're biased high somehow. We've improved our uncertainty, and we're biased high. So we kind of have a dilemma here. We eliminated the useless intercept and it improved our uncertainty, but because it narrowed down our uncertainty, we've lost the true value and we're biased high. So when we thought we were done and we had a good method for finding our true value, now we realize we don't. And so we kind of have a dilemma here. The statistical values improved and the uncertainty improved by getting rid of that intercept, but the accuracy got worse. It went from 0.8% high to 2.1% high. So which model do we use? We know the true value is 125, and the top one with the bad intercept got the right answer. Yes.
I think you'd use the second.
And why would you support that? So.
Just because it's, I guess the point is to like any analysis, you're trying to again, you want your numbers, I guess, to be close to the truth.
Mm-hmm.
I think it seems like kind of superficial to use like the bad intercept, like knowing that that's like a less accurate analysis, but it just happens to have wider parameters that.
Yeah. Yeah, and I mean, I see what you're saying. The argument you're making, it showed to be more accurate, but it's less something. It's not less accurate, but I think what you're trying to say is less defensible. Is that what you mean? Yeah, yeah, and I would agree with you on that. So he's saying don't use the first one, use the second one, even though the first one is quote more accurate. It hits the accuracy value. The uncertainty is within the true value is within our uncertainty, but we're using a bad B value. So I'm using moral language. If you're not catching that, I'm saying which one should you use? That word "should" is a moral word, right? I'm saying there's a right and wrong here. We've really reached a point where right and wrong are important, and also there's practical ramifications to being on the stand. And if you're asking you, why did you use the model that wasn't statistically defensible? You would say what? You would have to say because it gave the right answer. What was the right answer? The answer you wanted. Why did you want that answer? And so you've now stepped in a big mess. Okay, so for practical purposes, but also for moral purposes, you want to use the statistically defensible model. And that, I'm serious, but it says civilization depends upon this. This is, if you're starting to, think, well, I want to use the one that gives the right answer, that's the path to the dark side, right? Because you're letting yourself be biased. You're making decisions based upon what you want, not what you can defend. So this is a really important thing to point out. It's like, go with the null hypothesis and the statistics, and you can always defend your decisions, and you can sleep at night. Okay. So let's redo this now with standard addition. So the actual blood sample already containing 125 parts per billion cocaine is split into 4 analyses. Now this is really tricky because you have to take your sample and have to have enough of it to split. That's pretty easy if you've got a good blood draw. It's kind of difficult if you're trying to test, say, the ocular fluid or something like that. It's some really small amount of fluid. How are you going to split it into 4 samples? But, these instruments, they analyze, 50 microliter injections. So, maybe you'll be able to they even have inserts, like you've got a 500 microliter vial, well, they have like little plastic inserts that go in and reduce the volume to 200 microliters. So you can mix up samples that have 200 microliters, and then you can inject 50 of those. And so that's, you can get down to really small volumes, but that's the problem with standard additions is you have to take your actual sample and split it into parts. And then for each of those parts, you add the analyte in varying amounts to the analysis sample. So this is a difficult thing to defend sometimes because you took my client's blood and you added cocaine to it. Right? Well, you didn't add it to one of them. Okay, so there's a control there, and then you add it to the second, third, and fourth, and then you do this analysis. So this is a defensible analysis technique, but it sounds bad, doesn't it? You took my client's blood and added cocaine to it. So the x-intercept of the calibration curve gives the initial amount of cocaine that's present in the blood. So this is the calibration curve. Look how strange it looks. Our lowest data point, which we added 0 parts per billion of cocaine, is off the floor, right? And that means there was already cocaine in it. We didn't add any. There was already some there. And how do we know how much cocaine got it up this high? Is we do the x-intercept. And so where it hits the x-axis, that's how much cocaine was originally there. So this initial amount was present in the blood sample, and that x-intercept, the opposite sign of that, is going to be the amount that was in the blood. But it just looks weird. It's like, wait, my calibration curve is way, way high. So this is the regression analysis that we get, and look, our intercept, because the line is way off the x-axis, we have good statistics for both intercept and the slope. Okay. And so this is our calculation. We have our mx plus b, so we can solve for x, 125.42 parts per billion. The uncertainty is 0.23, really good uncertainty. Our CV is 0.2%, and the check value is 125, and our percent error is 0.3%. So this, our 95% confidence interval, so this is 1.96 times our uncertainty value, and then we subtract it from our mean and add it to the mean, and we have this range, 124.96 up to 125.87. So that's beautiful. So we are accurate and precise because we analyze the actual matrix of the blood. So this is a sort of roundabout trip through 3 different calibration methods with some spicy discussion about which model to use and why to use it. I started hitting you with moral language, okay? But this shows you how good things get when you have a good matrix match, a good analysis technique, and so on. You can hit things with a really tight window and know for sure with 95% confidence that this is a small range. It's between 124.96 and 125.87. So that's great. Any points you want clarified or things you want to bring up or discuss? We've got about 5 minutes. Okay. All right, so this is when the matrix effects were addressed, both the uncertainty and the accuracy improved. So, thank you. That's all we've got for today.